Hi everyone, in this session we're going to look at scheduling algorithms and multiprocessing. So first off, we'll look at some scheduling algorithm concepts. Some popular scheduling algorithms, we have 4 or 5 of them that we're going to look at. Operating systems scheduling management, so different operating systems handle things in slightly different ways. The idea and concept of multiprocessing. And then a little bit about process and thread scheduling. First off, a little bit about scheduling algorithms. So operating systems supporting multiple processes generally provide some sort of a prioritization mechanism. So a particular way of prioritizing one process or thread over another process or thread. And this algorithm must ensure that critical system processes execute at required intervals. And at the same time, the balancing act is that this operating system must also be responsive to user inputs. Like I mentioned in the previous session, any lag time from a user's perspective is not really acceptable. So several algorithms have been developed to meet these 2 main performance goals. So it's really a balancing act between making sure everything needs to be done for the system and then being able to also have a responsive system from the perspective of the user. So first come, first serve. This is what we call a non-preemptive approach, and it was common in old legacy batch processing operating systems. So one particular process would just grab access to resources and it wouldn't let go until it was done. So each process is granted control, here you go, and it keeps it until it's finished. There's no prioritization and no time limit. So back in the day, again, I'm aging myself here, when I was in college doing my undergrad in computer science, we did batch processing on a mainframe. And we would send a batch, and we would have to wait in the queue until our batch was processed. And then sometimes we'd have to wait a long time because someone else's code had gotten stuck in some sort of a loop and done what we called a core dump back then, and had basically tied up that mainframe for a long period of time. And so the system would need to be reset, and then we'd go to the next person in the queue. So it could sometimes take hours to get your batch job back from the mainframe room. We'd go down to a little opening in the wall where there would be a stack of execution jobs, and you'd find yours, and that would be your assignment. So purely dependent on the execution time of each process that's ahead of you in the queue. So on those old mainframe systems, it was very apparent when somebody's code had basically trashed the system, and we would ridicule those whose code had performed some sort of a core dump and had tied up the system. Anyways, that's the old non-preemptive approach, which we don't see so much anymore. So cooperative multi-threading, early versions of Windows and Mac relied on each thread to voluntarily give up control. And this could be a problem, right? How well designed was the program? Who wrote the code? If I wrote the code, for example, as an undergrad student, some Windows code, which we learned how to do way back when, how to write code for Windows, may not necessarily have been written so well. So it's an issue. So it requires significant effort and skill by the developer to ensure a balance between having access and giving up control. So poorly designed applications could starve other applications. And so the way that would appear, of course, to the user is serious lag time. So when control was given back to the OS, it would assign it back to the next thread, and we would go on in this process. So whenever you ran into a poorly designed application, it could really become quite apparent with the lag time seen from the user's perspective. So that led to better scheduling algorithms. First of these, round-robin scheduling, maintains a list of runnable threads, and it gives each thread its turn, and all priorities are equal. So you keep going down the list, and then you go back to the top again and start all over. So as long as a thread needs to be executed, it'll be part of that basic round-robin cyclical queue. The next is fixed priority preemptive scheduling. So the highest priority threads hit the front of the queue. And so this is great if you're a high priority thread, right, like a VIP thread, but lower priority threads may wait a long time. So if you think about this type of queuing, if you're at the airport and you're in the economy line trying to check in and some people come in the business line, you're going to wait while they get served, right? So if you're a high priority thread, great. If you're a low priority thread, you might be waiting a while. Next is what we call rate monotonic scheduling, or RMS. So it's a fixed priority preemptive style algorithm, but it's used in real-time systems with hard deadlines. So threads that execute more frequently are given high priority, so they're considered the ones that are to be more involved with real-time. Fair scheduling, priority determined by the amount of execution time consumed. So it's a balancing act between getting your processing done and how much processor time you use. So if you go over your allotment, or you're the most, have the highest amount of execution time, then you're going to spend more time at the back of the queue because of that. So the more that you use the processor, the more you use processing, the lower your priority will become. There's also multi-level feedback queue, where we have multiple queues and each has a different priority level. So similar to priority, it is a priority style. New threads are added at the tail of the highest priority queue, and as you use the processor more, you start to go into lower levels of priority. So you use your time slice, you go to the next lower priority, next lower priority. So again, it's the more you use, the lower priority you end up. So again, it basically is trying to optimize usage. So if your thread can use less cycles, right, then it'll effectively execute more quickly. So it gives a reward to being more efficient. Now, Windows Scheduler, so for the Windows operating systems, follows this multi-level feedback queue. So Windows and Linux process displays. I showed you last session the Mac activity monitor. Here you can see we have similar with Linux and Windows. This over here is the resource monitor for Windows. So you can see it's very similar to Mac. Here's our process IDs here. How many threads are running. So again, it's very similar interface, slightly different look and feel, but kind of the same information. How much percentage of the CPU is being used up. So you can see here the system is running quite a few threads, 256 threads currently. Dropbox in this example is also using quite a few threads. Turns out Dropbox is pretty thread heavy. And then a little bit of information about CPU usage, disk usage, network usage, etc. So that's Windows Resource Monitor. And then over here, more of a command line style is an example of Linux process display. So you run the right command to display processes. And you can see the same kind of information. There's your process ID over here. Here's your percentage of CPU here. You get the idea. Okay, so very similar type of information. Linux, Windows, and then last session we saw Mac. All right. Now, multiprocessing. So a multiprocessing computer, we call it multiprocessing, a true multiprocessing, right? If it has two or more processors, and that means that we can execute in parallel, so simultaneously. So processors typically share access to system resources, and when processors are treated equally, this is symmetric. So symmetric meaning equal. So symmetric multiprocessing. So each processor will process kind of the same amount of resources at the same processing speed. So in a well-designed system, throughput scales linearly with the number of processors. So you add a second processor, you get twice as much done. That's the optimal situation in a well-designed system. Now, a symmetric multiprocessing system is an example of what we call an MIMD, or a multi-instruction, multiple data architecture. And again, that's true parallel processing configuration. So the optimal is linear, right? One processor to two processors means you double, to three processors means you triple, right? A true linear progression. So each processor core operates independent instructions on its own set of data. We also have single instruction multiple data, executes the same instruction on multiple data elements simultaneously. So that's an SIMD. And modern processors, they implement SIMD on large data sets, such as graphical images, audio data sequences, right? Streaming, audio, and also streaming. Current generation PCs with multi-core processors can use MIMD, which is great. Now, and clock speeds have progressed, and this is, again, showing my age. I remember back to the megahertz days of processing speeds at low megahertz. Now we're at like 1,000 times, right? We're into the gigahertz. So clock speeds have progressed significantly. So the technologies and the process and the manufacturing abilities of chip manufacturers like NVIDIA, for example, have progressed so much that we're like 1,000 times faster than back when I was, again, I was a tech support person for a short period of time, using and fixing and manipulating old systems back in the days of soldering chips onto boards. All right. So just to summarize, that's all we wanted to talk about in this session. We talked a little bit about the concept of scheduling algorithms. We looked at some of the popular scheduling algorithms. Operating system scheduling management, so the different ones that are available. Talked a little bit about multiprocessing, and then lastly, the idea of process and thread scheduling, which was kind of mixed in with our algorithms as well. We looked at resource monitor in Windows, and then the command line version in Linux as well. All right, thanks for tuning in for this session, and we'll see you in the next session.